In this video, we're going to look at some examples for finding area between two curves. But before we get into the examples, let's just look at the concept behind what we're doing. Here you can see I've got a graph with two functions, f of x and g of x. Now, anytime that we're finding area of a region in calculus, what we're really doing is summing up infinitely many rectangles that can form that area. And so I'm going to draw a rectangle in here just to represent all those rectangles that we could draw. And the area of that rectangle is going to be, we're going to use the formula base times height. Now, whenever we draw a figure like this in calculus, if we're trying to find area, or later in future lessons when we start determining volume, our height is always going to be the horizontal distance at the bottom of our rectangle. And so in this case, if it's a rectangle that we can see, we're going to call that delta x. The base is this side of the rectangle. And so in order to find the area, we need to know how long the base is. Well, in this example, the way that I would find that length is to take whatever the function value is at f and subtract whatever the function value is at g. And that's going to give me the base of the rectangle. And then I want to sum up all of the rectangles to make that region. And if I was doing a finite number of rectangles, I could use this formula. But I really want to do an infinite number of rectangles. And so we're going to sum up the rectangles from A to B. The bases of the rectangles are going to be f of x minus g of x, and our height becomes infinitely small, and so we change it to a dx. And so this is where we get our formula for area. Now, one way that I would like us to think about this formula, I think a way that helps us remember how to apply it, is that the area from A to B is really going to be equal to the top function minus the bottom function. And in our example here, that happens to be the case that f of x is on top and g of x is on bottom. But it's not always that way. And so you want to make sure that you're always subtracting top minus bottom. Let's look at an example. We want to find the area of the region between y equals square root of x, y equals x plus 1, x equals 0, and x equals 1. So the first thing that we need to do here is to sketch a graph of the region that has been described. So I'm going to start with square root of x, and I know that that graph looks like this. X plus 1, that's going to be a linear function. See, I'll say that's 1. So a linear function crossing at 1. And then x equals 0. So let me see, I'm going to switch colors here. X equals 0, that's going to be that boundary there. And x equals 1, let's see, I'll say that's 1. And so that's going to bound off our region. So the area between those curves and between x equals 0 and x equals 1, well, that's this area right here. And so we want to find the area of that shaded region. All right, so we're going to integrate from 0 to 1. And remember, the formula I said is top minus bottom. And so in this case, the function that's on top is the x plus 1. So I'm going to say x plus 1 minus the bottom function, which is the square root of x. And then I'm going to put all that in parentheses, dx. And so there's our integral. We're going to go ahead and evaluate this integral by hand, do a little review of our integral rules. In order to integrate the square root of x, remember we need to rewrite that square root as, sorry, I was going to choose a different color, x to the 1/2. Remember, we can rewrite square roots as a fraction exponent. So we're going to think of that as x to the 1/2. So let's take this integral. The integral of x is going to be x squared over 2 plus the integral of 1, which is x, minus the integral of x to the 1/2, and that would be x to the 3/2 over 3/2, or that's the same thing as multiplying times 2/3. So that's the integral, and we want to evaluate from 0 to 1. Now when I go to sub these in, remember the 1 is going to substitute in first. So I get 1 squared over 2 plus 1 minus 2/3 times 1 to the 3/2. So that's substituting in 1 minus, and then I want to substitute in the 0, which is nice because when I substitute in the 0, it just all becomes, every term becomes 0. So really this part is just equal to 0. But I do need to, let's go ahead and simplify what we have over here. I've got 1/2 plus 1 minus, and I could rewrite the 3/2 as a root, but I really don't need to because 1 to any power is just 1 times 2/3 would be 2/3. And let's go one more step and combine those together. I need a common denominator, which would be, my common denominator would be 6. So I have 3/6. 1 would turn into 6/6, and then minus 2/3. 2/3 would be 4/6. And 3 plus 6 is 9 minus 4, 5/6. And so finally we have an answer here, 5/6, the area of our region. Let's look at a second example. Find the area of one region bounded by y equals sine x and y equals cosine x. So the wording of this problem is a little interesting, but let's sketch a graph and see if we can make some sense of this. So I'm going to sketch sine x first. Mark this off. That would be pi. This would be 2 pi. And then I think I'm going to grab another color and sketch cosine. Let's go back. Pi over 2. 3 pi over 2. All right, so now let's sketch cosine. So here we can see that we've got a region that's bounded by these two curves. This region right here. Now if I had extended the curves, let me extend them a little bit. Cosine would keep going that way. Sine would go like that. Notice that that forms another region. And if I had drawn a more accurate graph, you might be able to tell that these two regions would actually have the same area. That's just a reflection of each other. But we're just going to find the area of this first region. Now notice in our problem this time, they don't give us the x values. In our first example, we had x equals 0 and x equals 1, but this time we don't. But our x values are going to be these intersection points on our graph. We need to figure out what x's correspond to those intersection points. So remember, this is a graph of sine and cosine, and so what I need to think to myself is, where are sine and cosine equal to the same thing? Because if they're intersecting, that means they're equal. Well, that of course happens at pi over 4, because cosine of pi over 4 is square root of 2 over 2. Sine of pi over 4 is also square root of 2 over 2. And then the other place where they're going to be equal, at this point down here, that happens at 5 pi over 4. That's in quadrant 3, where cosine and sine of 5 pi over 4, they're both equal to negative square root of 2 over 2. So now I have my x values for my integral, and I think we're ready to find this area. I'm going to erase some of this graph so that I've got a little more space here. Alright, so we're going to integrate from pi over 4 to 5 pi over 4, and then our formula tells us that we want to do top minus bottom. So if I go back and look at the graph, I want to figure out which graph is on top, and it looks like the sine graph is on top. Sine x minus, and then the bottom graph is cosine x dx. All right, and again, we're going to do this by hand, review our integration rules. The integral of sine is negative cosine x minus the integral of cosine, which is sine x. And I want to evaluate that, whoops, not 0. I want to evaluate from pi over 4 to 5 pi over 4. So I'm going to substitute the top number in first. Negative cosine of 5 pi over 4 minus sine of 5 pi over 4 minus, and then we need to substitute in the pi over 4. Negative cosine of pi over 4 minus sine of pi over 4. All right, and now the unit circle comes into play. Cosine of 5 pi over 4, well, I know cosine of anything over 4 should be square root of 2 over 2. 5 pi over 4 is in quadrant 3 where cosine would be negative. So this becomes negative square root of 2 over 2 minus, and then sine of 5 pi over 4 is also negative square root of 2 over 2. So I have negative square root of 2 over 2 minus negative square root of 2 over 2. Sorry about that. Let's move over to the next one, minus. And then cosine of pi over 4 is just square root of 2 over 2. So negative square root of 2 over 2 minus sine of pi over 4, which is also square root of 2 over 2. So in my first parentheses here, if I have minus and negative, both of those turn into, let me fix that, turn into positives, and these turn into positives. And so in this first parentheses, I end up with 2 square root of 2 over 2 minus, and then in the second parentheses, I have negative 2 square root of 2 over 2. Minus the negative would become plus. And actually I could reduce, I can cancel those 2's. So really what I end up with is square root of 2 plus square root of 2, or 2 square root of 2. And that would be the area of our region. I've got one last example for us. Find the area of the region bound between f of x is equal to 3x cubed minus x squared minus 10x, and g of x equals negative x squared plus 2x. Now this is a question that you can do in your calculator. So if you want to get out your calculator and enter those two functions, one of them into f1 and the other one into f2. And when you do that, we're going to get a graph. That looks like this. Okay, I probably should have used different colors. I'm going to go back over. So I'm going to let that graph, what I just covered over in orange, be g of x. And this first one, the cubic graph here, that's going to correspond to our f of x. All right, so if I'm just looking for the area of the region between these curves, notice in this picture that we've actually got two regions between the curves. There's this region here, and there's also this region here. And if I look at the first region, notice that the green graph, the f of x graph, is on top, and the orange graph is on bottom. The cubic graph is on top, the quadratic graph is on bottom. But when I look at the second region, the top graph is actually the quadratic graph, the orange, and the bottom graph is the green graph, or the cubic. And so what that means is that my top and bottom are switching as I go from one region to the next. And so here we're going to need to do two separate integrals, one for each region on its own. Now before we do that, we need to find our intersection points. I don't have any x values given to me, and so I need to find the values of the three intersection points. And you can do that on your calculator. If you use the intersection feature on your calculator, you're going to find out that this point has the coordinates -2, -8. This point is 0, 0, and this point over here is 2, 0. So now let's set up the integral to find our area. We're going to do the first region first. So we need to integrate from -2 to 0. Remember that the little numbers on our integral, those are always x numbers. And so in this case, I'm starting here at -2 and I'm integrating to 0. And for that region, the top function is the cubic function, which I'm just going to call f of x, minus the bottom function, which is g of x, dx. So that's going to be our first region. And then we want to add to that plus, and for the second region, I'm going to integrate, this time starting at 0 and stopping at +2, +2 being the x-coordinate of our last intersection point. But this time when I do top minus bottom, it's the g of x function that's on top, and the f of x function is on the bottom. And so the sum of these two integrals is going to give us the sum of the two regions. Now you can do this in your calculator, and remember, if you've entered, hopefully you entered f into f1, and if you entered g into f2, then when you type this integral into your calculator, you can use that notation. Let's just call this f1 of x minus g1 of x. And then, I'm sorry, not g1 of x. That would be f2 of x. And then when you do your second integral, you need to do f2 of x minus f1 of x. And when you put all that in, if you've done it correctly, you should end up with an answer for this region, the sum of regions, area 24.